Okay, so welcome back, everybody. Yesterday's lecture, if you haven't had a chance to have a look at it yet, I encourage you to do that pretty soon because that material is going to be important for understanding how these functions behave. This is kind of going to be your basic understanding of what a function of a complex variable is doing. But moving on, right, we want to essentially do calculus on functions of a complex variable. That's really what this course is about. And so if you're wanting to do calculus, then you have to discuss limits, okay, the notion of taking limits here. All right, and so when I say that the limit as complex number z approaches some fixed complex number z naught of f of z is equal to some w naught, what do I mean? What is the definition? So the epsilon delta definition, right, mimicking the epsilon delta definition of like Weierstrass originally for calculus and functions of a real variable, is this: for each epsilon greater than 0, so epsilon greater than 0 is just some positive real number. Okay, there exists, right, so there exists some positive real number delta such that the modulus of f of z minus w naught is strictly less than epsilon whenever we have, so whenever we have that z minus z naught, or the modulus of z minus z naught, is strictly between 0 and delta. Okay, so this is the epsilon delta definition of what it means to say that a function f of a complex variable has w naught as its limit. So the limit of z goes to z naught of f of z is w naught. That is what is meant by this. Now, more informally, what is meant by this? Like, what does this epsilon delta definition mean? If you recall, this idea from calculus is that we can make this functional value arbitrarily close to w naught if we choose a point close enough to this z naught. Okay, but still different from it because this is a punctured disk, right? So the idea is let f be a function defined on a punctured disk centered at z naught. Okay. Okay. Well, a punctured disk centered at z naught. Here's an example of one, right? Here's such a punctured disk, right? So recall when we were defining these sets, this was exactly what we used to define a punctured disk. The idea here being that we want to talk about a function defined on a punctured disk because we want to apply this to situations where the function f may not be defined at the point z naught itself, right? And so that's why it's a punctured disk. That's why z naught itself isn't included here. Okay. The idea is that when we say this, I'll call this star. So when we say star, okay, we mean that the value of f of z can be made arbitrarily close to w naught, okay, by choosing z close enough to z naught. But of course, not necessarily equal to it, right? But not equal to z naught. Okay, this is the idea behind the epsilon delta definition. All right. Now, this had a nice interpretation when you're talking about functions of a real variable, because we could draw this delta window, right, was an interval on the x-axis, and we could draw this epsilon window up above. It was a window, an interval on the y-axis, right? That's how you could see this, and you could see it as a squeezing type argument. That's where the epsilon delta definition comes from, or that's rather the motivation for it. But here, for function of complex variable, we don't exactly have that picture. We have a picture that actually mimics the situation for talking about limits of functions of real valued functions of two variables. So we'll see exactly how that relates here in a second. But the picture here then is the following. So I have the Z complex plane, or the one where my real and imaginary parts are x and y. And so I have, say, some punctured disk, centered at z0. Okay, maybe this is what it looks like, right? Where my radius is my radius of this disk is delta, and maybe here is the value z that I'm choosing. Okay, and then to see the picture in the image, I am over in this UV plane, and what this statement, let me draw the epsilon ball here. So the epsilon ball is this one. It is centered at W0. Let me bring this back for a second. So here's my definition, right? So I have a punctured disk centered at Z0. That's what this is describing. Here, this is an epsilon. This is an open disk centered at W0 of radius epsilon. So here is my W0. The radius is epsilon. Okay, and here is, say, my W, where f of z is equal to w, and I have this mapping. Now, what does this imply? So going back to this statement, right? So here, let me fold this so I can get them both on the same page. So for each epsilon greater than 0, there exists a delta greater than 0 such that this is true. So f of z lies within this epsilon ball centered at W0 whenever z lies in this delta ball. Okay, so what is it saying? It's saying that any point, any z that lies in this delta ball, its image has to lie in this epsilon ball somewhere. Now, it doesn't mean that the image of this punctured disk has to be the entire epsilon ball. It doesn't have to fill out the epsilon open disk or anything like that. It just has to sit inside it. Okay, so the image of this thing sits inside this epsilon open disk. And now you see why it's important, before we talked about this, to discuss thinking of these functions as transformations or mappings, because it's hard to parse through any of that if you don't understand this interpretation. Of course, if that statement is true for some delta, so if it's true for some delta, then it would be true for anything less than delta, right? So it would be true for a punctured disk centered at z0 of any radius less than delta, so it would be true for delta over 2, delta over 3, delta over 4, and so on. Okay, and again, all it's saying is that the image of this thing, so under f, is contained here. So it's entirely contained. So maybe it looks like that, right? Or is entirely contained in this ball. It doesn't have to fill it out. It doesn't have to be equal to it. Okay. All right. Now, there's some facts about these limits. We're not going to prove many of them because it turns out that after we have, especially one of these facts, basically all of the limit theorems that we're going to talk about, these basic algebra of limits, those proofs are going to follow the exact same proofs for real valued functions of two variables. And we'll see how that works in a little bit. But I wanted to state one fact that I'm also not going to prove, and I may have you do in this homework that I'm going to post today, which is the following. So this f has three things. So a fact here. When the limit of a function exists, so when the limit as z approaches z naught of f of z exists, so we say that that limit exists when it satisfies that condition star that, or the condition in the definition of star that I just took off the screen. So when this limit exists, it is unique. This actually has something to do with topological properties that I won't get into. But I'm not going to go through the proof of this. Like I said, I may have you all replicate that proof, but you can just take it as fact that whenever the limit exists, it is unique. And so at a point, a function has to have, if you can find the limit that a function has at some point, then any other computation of the limit at that point has to be the same. So once you've found it, that's it. There's no other option there. So let's do a basic example here. Okay, just to show you how you would deal with epsilon delta stuff. We're not going to be doing much with epsilon delta stuff because we're gonna get more to the meatier stuff, because you've already basically all of the algebra you've done with limits in the past forever ago in like Calc 1. That's more or less what's going on here, just slightly more general. So example, we can notice that we defined this in a way to talk about a function having a limit at points, say centered at so this punctured disk here. So the point is taken as the center of the punctured disk here. But we can actually talk about the definition of a limit when you have a boundary point of a region. So we can also extend the earlier definition to include the case of limits at boundary points. Okay, an example to show how to do this follows. Maybe I've run out of room here. So, okay, so here's an example of how to do this. So let f of z be the following. Let this be I times z bar over 2. Okay, defined on the open disk. All right, so this is an open disk of radius 1. Okay. Then I want to compute the limit as z approaches 1 of f of z. So what is that? Okay. Let's draw a picture here. So in my picture, if I'm thinking of, say, so we're talking about f defined on this open disk. So here's my open disk of radius 1. Okay. Now, here is an issue, because the point that I want to approach here is 1, which is a boundary point of this domain of definition. Okay. So then how do I parse that with the definition that I had before? Right? Well, the idea is to look at a punctured disk centered at the point that I'm approaching, just as before, and a suitable sized, we'll mention the radius here in a second when we figure out what it needs to be, but a suitable sized epsilon neighborhood or punctured disk centered at 1 here of some radius. Okay, the candidate points, right, that we take in this definition would be the points that are in the intersection of these two. So it would be points that belong to the overlap here. Okay, so our z we take to belong to this overlap. All right. Okay, so if z is in the unit disk, then first of all, I look at this and I do the thing that I like to do when I'm dealing with limits. I look at this and I try to guess what this should be. Right? So if I look at this, limit z is approaching 1. So if z is really, really close to 1, let's just say that z is equal to 1 right here and see what is going on here. So when z is equal to 1, it's real, so its conjugate is just 1. And so this should be I times 1/2, or I over 2, right, if my naive analysis works here. So I guess that this is I over 2. That's my guess. And now I'm going to use the epsilon delta definition to show that this is indeed what happens. So when z is in the open unit disk, so when modulus of z is strictly less than 1, then if we look at the modulus of f of z minus I over 2, what is that? Well, f of z is I z bar over 2 minus I over 2, right? Okay. And so this is modulus of, so this is, I can actually factor out an I over 2 here. So this is modulus of I over 2 times, this is going to be z minus 1, if you like, or z bar minus 1. So this is z bar minus 1. When I apply the modulus here, this is actually, the modulus of I is 1, and the 1/2 comes out. This is modulus of z minus 1 over 2. Okay. And so, for the way that this works is we say for some arbitrary epsilon greater than 0, epsilon has to be arbitrary. Delta is the thing I'm allowed to choose. So if epsilon is positive, okay, then choose delta to be 2 times epsilon. Then if z minus, or the modulus of z minus 1 is strictly between 0 and delta, then this quantity, modulus of f of z minus I over 2, is equal to modulus of z minus 1 over 2, which is strictly less than delta over 2, but that's equal to 2 epsilon over 2, which is epsilon. So this is strictly less than epsilon, and we're done. And so this limit is I over 2. Now, I don't want to focus too hard on this stuff because I'm not going to have you doing too much with epsilon delta stuff. This is just the machinery that's going on under the hood. And so if I was going to draw that same picture, what would the image look like? So if this is my domain here, what would the image of this look like? It would be at so the epsilon ball would be centered here at I over 2, right? And this is in the UV complex plane. Okay. Okay. Right, and so my mapping of, say, this point Z would be like, it would be here, maybe. It would be somewhere in that ball. Okay, this is, again, just a formal way of saying that we can make our functional values arbitrarily close to that value if we pick them close enough to the point in question. Okay. Now, one warning, caveat slash big fact, maybe I'll just say this is a star fact. And you will have likely seen this previously you will have seen this in Calc 3, definitely, or any other place that had you talking about limits of functions of two or more variables. So when we talk about the limit as z approaches z naught of f of z, well, let's put z naught here. Now the question is, how am I allowed to approach this? Well, when you have looked at things like this, like I said before in the past, you might have seen that, well, there's some standard ways, right? So I could approach it from the left, or I could approach it from the right. But you see, from the left and right was kind of the only directions that we could approach things in Calc 1 because we had a function of one variable. So we were in a one-dimensional set. So that was the only, that was the only room there was for different directions. Okay, but actually, I am allowed to approach this from any direction. And it's not that the notion of limit is like stricter or stronger for things like this or for multivariable functions. This is actually the exact same definition. It's just that in one dimension, there's just not enough room to see all of this going on. In fact, these aren't the only, I don't have to be so rigid here. I can actually approach this by a curve. I can approach this on, some curve like that. I'm actually allowed to approach this point from any nice enough path. Okay, so I can actually, so this can be computed. Well, when I say that, it means that I'm not saying that, you can pick some horrific curve and you can definitely compute it in that way. I'm just saying that it can be computed by approaching it in an arbitrary way. I.e., along a general path. Okay. This is something that you learn. This is likely one of the few examples that you work through in Calc 3 when you're first doing limits of functions of two variables. Because there's some nice examples there. This is going to be typically used to actually show that something doesn't have a limit at a point. Okay, so to see that, let's let f of z be z over z bar. Okay, so let's let f of z be z over z bar. All right. I want to compute the limit as z approaches 0 of f of z. What is this? Okay. Well, to see what this is, what I'm going to do is consider two cases. Okay, so here is my origin. There's 0. So I'm going to have two ideas here. The first idea is to have this approach down the y-axis. Okay, so I start at a point here. Of course, a point on the y-axis is a point 0, y. Okay. And then I'm also going to compute this same limit approaching in another way, approaching from the x-axis, say the positive x-axis, from a point x0 going to 0, 0. Okay. And so we'll call this first path, I'll call this first path path A. I'll call this second path path B. The notation I'm about to write is not in any way standard or typical. I'm just doing it to keep track of this. Okay, and so I want to compute the limit as z is going to 0, 0 along the path A, right, of f of z. Okay, and so this is the limit as z is approaching 0, 0 along this path A of, so f of z here is z over z bar. If I write that in terms of x and y, this would be x plus iy over x minus iy. Okay, but so here then, I'm going to have points that look like 0y. So really that's what I'm computing. So I'm using the limit of points 0y approaching 0, 0 of x plus iy over x minus iy. So my x coordinate, of course, is 0 here for all of these. And so this is going to be 0 plus iy over 0 minus iy. Well, what is that? That's minus 1. So you might be tempted to stop there. If you're trying to compute this thing as, if you're trying to compute the limit of a thing like this by approaching along a path, you've found a number here, and maybe you're tempted to stop. The thing I want to, ensure about this, or ensure that you understand about this, is that it's not enough to just pick a path, okay, and compute this thing. The idea is that any computation done here has to match up with any other computation. You can't just pick the path you want and say, oh, now I found that the limit is a particular number, and I just stop, right? It actually has to match up with every other path here. So maybe this is worded a little awkwardly. So I should stress that you can't do this by just picking a single path and being done with it. You actually have to figure out how this works from the definition, because this has to match up. It doesn't matter which path you use. It has to match up. Okay, and so let's do it approaching along B. So what is the limit as z approaches along B, this point 0, 0 of f of z? Well, I don't have to go through all of this again. I can just say this is, so here we're using points x0. So this is x plus I0 over x minus I0, which is 1. Right? And since we're allowed to compute this along any path that we want, we computed it along this first path, we got minus 1. We computed it along the second path, we got 1. These would need to match up. These are not equal. So what does this mean about this limit? It does not exist. D and E, right? Your favorite phrase. Okay, so that limit doesn't exist for that reason. Okay. So this can't be used for directly computing limit. So can't be used to directly compute limit. Okay. But it can be used in instances like this if you suspect, typically one of the nicest ways of showing that a limit doesn't exist is exactly this kind of trick, to basically pick two paths judiciously that are going to give you two different limits. Okay, at that point. All right, and now we want to discuss the some basic facts about limits, since you might look back on what you've done with limits in the past and you say, well, you know what, I didn't do a whole lot with epsilon delta, which is the actual definition of limits. And typically what I did with limits was I used some kind of theorems, right, that told me what certain limits were of algebraic combinations of functions. And then, like, whenever I needed to compute a limit, I just used those theorems, either directly or I was implicitly using them. Okay, and so the main thing, so I'm not going to prove almost any of these that we talk about, because so the first one is important because it basically puts us in the world of real valued functions of two variables. Okay, and that's why I was mentioning that before. And so there's a very important theorem. It's called Theorem 1 in this section in the textbook. But there's the following theorem, which says, suppose, we'll just set up our notation here, suppose that f of z is already written in its form u of xy plus I v of xy. Okay, of course we're thinking of z as x plus iy. Okay, let's say that z naught is defined to be x naught plus iy naught. Okay, and we'll say that w naught is defined to be u naught plus I v naught. Okay, here is the big statement. Then the limit as z approaches z naught of f of z is equal to w naught if and only if the limit as xy approaches x naught, or x naught y naught of u of xy is equal to u naught, and the limit as xy approaches x naught y naught of v of xy is equal to v naught. Hey, this is really nice. This says that a limit of a function of a complex variable existing, okay, boils down to limits of real valued functions of two real variables existing. Or I should say, yeah, to limits of real valued functions of two real variables existing. And what is nice about this is that you have already, in your mathematical lifetime, you've already seen examples of these things. Okay, so you've already seen examples of those things, and because of that, we can actually have a lot of mileage already taken care of from these limit theorems that were proven in those courses. Okay, because actually questions about limits here reduce exactly to questions about limits of real valued functions of two real variables. Okay. Now, if you're asking yourself, when does the when does the difference come in? Well, we've already seen the difference in how we have to consider thinking about functions of a complex variable graphically, but we're quickly about to see why this is not the same as the move from like a scalar valued to vector valued, and how you can move everything to the components. It doesn't work out like that. So we'll see exactly what happens with that going forward. And so the nice big mega theorem that describes all of these nice algebraic properties of limits. So algebraic properties of limits. These are the things that you might recall from Calc 1. And these are all proven in the same way they're proven in Calc 3 for functions of two real variables. Okay, and so suppose that we have two complex valued functions of a complex variable, little f and big F. So suppose that the limit as z goes to z naught of little f of z is w naught, and the limit as z goes to z naught of big F of z is equal to big W naught. Okay. Then we have the following three facts. So 1, what is the limit of the sum? We get to say some really cool things. Our favorite types of statements to make in math, right, is this symmetric type statement. The limit of the sum is the sum of the limits. Right? So the limit as z goes to z naught of f of z plus big F of z is the sum of those limits. It's little w naught plus big W naught. Secondly, the limit of the product is the product of the limits. Right? So the limit of the product, little f times big F, is equal to little w naught plus big W naught. Okay. And the limit of the quotient so f of z over big F of z. This is the quotient of the limits so long as big W naught is not equal to 0. Okay. Okay. So you can actually prove this without the theorem 1 that I just stated previously. You can definitely do that. You can do this strictly from the definition if you like. And it's actually very similar to how this would work in Calc 1. But it's even easier with theorem 1 because you already have a ton of theorems about real valued functions of real variables when it comes to limits. And so I'm not going to prove these, but I could say the proof is either using definition of limit for f of z, or by using the previous theorem and applying limit theorems from Calc 3. Okay, those are your options. Okay, I want to make one statement that we can immediately conclude from these. And then I'm going to go on to a more conceptual topic that's very important for what we're going to do going forward, because it is another example of a key difference between doing analysis with functions of a complex variable. It's actually one of the cooler things that we can talk about. Okay. So note, if we have a polynomial, all right, p of z is a polynomial, so it's a naught plus a1z plus a2z squared, and so on, all the way up to some a sub n z to the n. Right. Well, this polynomial is really just constant function plus a constant times z plus a constant times z squared. So it's really linear combinations of functions that look like this, right? So really a polynomial is just linear combination of these monomial functions that are just constants times, z to the n. But even that is just z multiplied by z a bunch of times, right? Why am I writing out these obvious facts? Because from that previous theorem, I can already compute this. So from the previous theorem, all I need to know, so if I know that the limit as z approaches z naught of a constant is that same constant, and the limit as z approaches z naught of z is z naught. So if I know those two things, which you can easily work out either just intuitively or you can do it straight from the definition if you like, If I know these two things, then the limit as z approaches z naught of p of z, this polynomial, is the limit as z approaches z naught of that thing, right? A naught plus a1z plus a2z squared, and so on, plus a sub n z to the n. Okay, well, according to my first fact, right, and of course I can, more generally, it's not just the sum of two functions. I could sum any number of functions here. I could prove that with induction, that this breaks up across any number, right, any finite number of functions here summed together. I can do this, and so I can split this up by number 1, right, split this up by number 1. So this is, limit as z approaches z naught of a naught plus limit as z approaches z naught of a1z, and so on. I'm not going to write all those. So limit as z approaches z naught of a sub n z to the n. Okay. But now, well, I know what the limit of constant is. It's just that same constant. Limit of z is z naught. I can use the fact that the limit of a product is product of the limits. So this gives me that this is a naught. Here I would have the limit of a sub 1, which is just a sub 1, times the limit of z goes z naught of z, which is z naught. So this is plus a1 z naught, plus a sub 2 z naught squared, and so on, all the way up to a sub n. This would be z naught times z naught times z naught, using number 2 from that previous theorem. So this would be z naught to the n. Oh, but that's actually just p of z naught. Okay. So if I had a polynomial, right? If I had a polynomial, then the limit as z approaches z naught of that polynomial is just that polynomial evaluated at z naught. This is our first example of a special type of function here, right? Or this is the first general example of a special type of function that I'll get to here in a second, right? You already know this is the notion of a continuous function. Okay, and so we'll be back to that in a second. All right. Now, what about limits involving the point at infinity? Even phrasing it this way is already hinting that there's something a little bit different going on here. And this, what I'm about to explain now, is one of the nicest characterizations of some type of phenomena that's going on that you're going to get in math. There's a ton of stuff like this. This example I'm about to mention is it does a ton of legwork and can lead to a lot of understanding here. And this is the following notion. So it is useful to think of what is called the extended complex plane. So the idea is, let's start out with my complex plane C. Okay, so whether you think about this complex plane as being C or R2 doesn't really matter. I have axes here, so here's my x-axis, here's my y-axis. I'm not going to draw them all the way, and this plane, of course, is continuing on indefinitely. Okay, so here's my complex plane. Now, it is useful to think of course, this thing is going off in all directions indefinitely, but it's useful to think of this plane. Maybe I'll shade it to indicate that I'm thinking of the entire plane here. So here's my plane C, complex plane. It's useful to think about this plane together with a point not on the plane. So here's my point. This is a point not on C. Okay. So we have a point that's not on C. Now I'm going to name this point. I'm going to name it as a symbol. I'm going to name it infinity. Okay. I'm going to name it infinity. Now I have complex plane, point not on the complex plane. I consider taking the complex plane together with this point that's not on it that I'm calling infinity, combining them together, and I write this as the complex plane union this point that I'm calling infinity. This is called the extended complex plane. Okay. This is also can be thought of, so I'm going to call it the extended complex plane in this class. This is also the, and I'm not going to go into what this is a topological construction. This is called the one-point compactification of the complex plane. So this one-point compactification, that's its own construction. You can talk about the one-point compactification of a more general space, but this is just applying it to the complex plane here. Okay. Now, in this picture, it turns out that this one-point compactification, or this extended complex plane, can be thought of as I have my entire complex plane that has all my usual complex numbers, but we know that this plane goes off to infinity in all directions. So what does it mean to go off to infinity? The idea is to think about this plane going off to infinity at all directions, but we are calling this point infinity, and so we like to think about this as it goes off, it eventually wraps up to this point. Okay, so at infinity, right, which is literally, at this point that I'm calling infinity, C wraps up to the point infinity from all directions. Now, it turns out that this one-point compactification, or this extended complex plane, it turns out that we can view this extended complex plane, C union this point at infinity, okay, to be the two-dimensional sphere. Which we'll call S2. Another way of saying this is the one-point compactification of the plane is a sphere of radius, or, well, it doesn't matter what the radius is, a sphere of dimension 2. Okay. We're going to see exactly how to see this explicitly. Okay. Now, you might stop me here and say, why are we doing this? The nice thing about this is that we are going to be able, in considering the extended complex plane, we are going to be able to actually have a point that we're calling infinity that we can do algebra with. Okay. Remember how it is a little weird to do algebra with infinity. If you talk about the extended reals, right? Or if you're just trying to deal informally with infinity, this could get a little awkward doing some of the algebra, right? You end up with a lot of expressions that you can't really figure out exactly what's going on if you're not careful. So you might remember that. Well, here, what we're trying to do is make it so that we can basically do algebra, if we're careful, with infinity. We can treat this infinity just like any other point in the complex plane. It just has a few special rules. Okay, so that's the reason why we want to do this. To see this picture, here is the idea. So to see the identification of the extended complex plane, C, together with this point at infinity, with the sphere S2, we use stereographic projection. Now, there's a number of ways that you don't have to do it in exactly this same way that this is being done. I'm going to follow how the textbook does it, but this is the way that I learned it originally. It was slightly different. And so I'm going to say, let's say we have our complex plane. Okay, so our complex plane looks like that. Okay, and let's pick our origin complex plane. So here is our origin. Okay, what I want to do is think about a sphere that is centered at my origin here. And so it is centered at my origin, and the complex plane is going to cut right through its like canonical diameter here. It's going to cut right through the equator. Okay, and so if here is my sphere, right? So here's like the equatorial circle of my sphere. Here's the top hemisphere, and here's the bottom. Okay, you don't have to do it this way. As I said, you can actually have the sphere sitting at the origin. So the picture could look like this. So you have complex plane, here's 0, and the sphere sits on top, so that its bottom, the south pole of the sphere, is actually the origin. Okay, you can do it that way. You can do it this way. It doesn't actually matter how you do this. Okay. All right. Yeah, there's a formulation you can use where the sphere is here. You can absolutely do it this way. I'm going to do it this way just because this is the picture that is drawn in the textbook. If you wanted to see, if you wanted to look at that yourself. What is the idea with stereographic projection? Okay, so the idea is that I select the north pole. Here's my north pole, okay, of the sphere. Okay, and if I want to see this identification of the extended complex plane with the sphere, then I can go both directions. So this stereographic projection map is actually going to provide the whatever morphism you like between these spaces. So if you want to think about it as an isomorphism, or whatever map gives you the equivalent structure that you're looking for. Okay, that's what type of map it is, because I can go forward and backward. So what I mean by that is if I think of starting with a point on the complex plane, and I ask myself, what point on this sphere is associated to this point in the complex plane? Well, I'm missing my straight edge again. Hold on one second. Always a fight for the straight edge. Okay. All right, so what we would do is we would draw a line from the North Pole to this Z. This is our stereographic projection line, so we're projecting from the North Pole. This is explained a lot of times as thinking of shining a light, right, in this direction. This has to intersect the sphere at a point. We'll call that point P. Okay, that point on the sphere is the point associated to the complex number Z in the plane. And now that you see that, I can go in the other direction. Okay, what do I mean? I mean that if I start with sphere now, so I'm going to do it in this other picture here. So if I start with sphere, okay, then if I start with a point on the sphere, say here, right, here's my point P, and I draw the projection line from N to P through until it intersects the plane. It intersects the plane at some point. It's hard to see due to perspective here, but we'll say that it intersects the plane there, and this becomes a dashed line after that. That's what I should have done, okay, to make that make sense. Then this would be my point Z there. So I can go in both directions. I can specify a complex number that is associated to a point on this sphere that I've drawn here. Similarly, I can specify a point on the sphere, and that specifies a complex number. Okay. All right. And so, this map that I've drawn is called Stereographic Projection. And this sphere is called the Riemann sphere. So this sphere, S2, in this particular example, is called the Riemann sphere. Okay, this is like a fundamental object in complex. Okay. And so now we have a nifty statement. So basically, you can think of any point, right? So any point on C, right, comes from stereographic projection. From the Riemann sphere, from the north pole of the Riemann sphere. All right, in this way. The question then is, what point on the Riemann sphere does the point infinity come from? So any point that I would pick on my complex plane, no matter how far out, maybe I'm all the way out here, right? I would still say that comes from projection of the Riemann sphere through some point. Now notice, the further out I get, the closer these projection lines are to being tangent to my sphere, until eventually there of course is a projection line that is exactly tangent through the North Pole out like this. Okay. That projection line projects to infinity. So the answer is the North Pole. And so this, it might not seem like much at first, but this gives you a very, very nice way of quantifying infinity. In a way that, you know, people had struggled with doing for thousands of years, the notion of infinity. It puzzled mathematicians, but being able to say, oh, infinity is just this point that the North Pole maps to under stereographic projection of the Riemann sphere, right? So there it is, right? I can even draw it, right? And of course, as long as this point doesn't lie on my complex plane, then that's valid as a choice for infinity. So infinity for us doesn't have to be a thing that you can't see. You can actually just draw it right here, right? There it is. There's the point. Okay, this is extremely useful for doing analysis and some algebra involving these complex functions. Okay, so this might not seem like much the first time you see it, but this is actually really, really nice. Okay, and so let's look at some terminology here. So if we are looking at if we're looking at points on the sphere that are close to n, maybe that's what we should think about here. So here's my origin. Here's a nice characterization. Here's my origin. If I think about this sphere as being a unit sphere, right? There's no reason why I couldn't do that. Then actually I can see exactly how to nail down points, right, that up here on the sphere are really close to n, right? These would be points satisfying. So notice if, say, epsilon greater than 0 is small, all right, the points in the complex plane belonging to the exterior of the circle modulus of z is 1 over epsilon, right? So we're dividing by epsilon, it's small, so this is a huge radius. Okay, correspond to points close to n on the Riemann sphere. So let's think about that for a second. So let's imagine that, you know, we have it scaled such that a point out here is like really, really huge. So a point out here would have like real and imaginary parts that are like, you know, 10,000 digits or something, right? Then cutting off some huge circular radius, these points here would come from points on the sphere very close to n, right? These points way out here would come from points very close to the North Pole. Okay. All right. And so they would be to the exterior of this, or they would belong to, say, a set modulus of z is greater than 1 over epsilon. Okay. So we call this an epsilon neighborhood of infinity. Okay. Or a neighborhood of infinity. Or we would maybe say that these points are close to infinity because they're close to the North Pole on the Riemann sphere. So they are out near infinity. Okay. All right. So now we actually, there's a reason why we wanted to talk about epsilon neighborhoods of infinity or neighborhoods of infinity. Now we can define the expression, the limit as z goes to z naught of f of z is equal to some value w naught for some of these values being infinity. So z naught could be infinity, w naught could be infinity, for z naught or w naught possibly infinity. So this is important, right? How do we do this? We just replace the usual neighborhoods with neighborhoods of infinity. It's that simple. Okay. And now that we have said that, we actually have some statements here that immediately show how we can apply this. Okay. This is kind of the important bit. Okay, so here's the theorem that ties some of this together. Okay, so if z naught and w naught are points in the z and w planes respectively, so this is respectively, then a couple of facts. So the first one, the limit as z goes to z naught of f of z is infinity if and only if the limit as z goes to z naught of 1 over f of z is equal to 0. The limit as z goes to z naught of f of z, I wanted to actually do one of the infinity limits here. Oop. Let me redo this. So the limit as z goes to infinity, rather, of f of z is equal to w naught. What does that mean? This is true if and only if the limit as z goes to 0 of f of 1 over z is equal to w naught. Aha! Okay. So actually, if you don't like dealing with taking an infinite limit, you can actually just replace it in this way, right? This is actually the same thing. Lastly, what does it mean if the limit as z goes to infinity of a function is infinity? Well, this happens combining the previous two if and only if the limit as z goes to 0 of 1 over f of 1 over z is equal to 0. Okay. So this actually gives nice ways of characterizing limits involving that point at infinity. Okay. All right. Let's do a couple of these. Let's do a quick example to actually show us using some of this before moving on. So here's an example. Let's compute the limit as z approaches minus 1 of I times z plus 3 over z plus 1. Okay, what is that limit? Well, whatever that is, notice that, so what is this? Notice that the limit of the reciprocal as z approaches minus 1, so the limit as z approaches minus 1 of the reciprocal, which is, so we'll just go ahead and write it as z plus 1 over I z plus 3. What is this limit? Well, I can kind of straightforwardly compute, I can just plug in minus 1 here using my limit of quotient is quotient of limits here. So I can plug in minus 1 here to get that this is 0. So the limit as z approaches minus 1 of the reciprocal of the function is 0. So then the limit as z approaches minus 1 of the function itself is infinity. From fact number 1. Right, so by applying fact 1, I can tell that this limit is infinite because if I look at the limit of the reciprocal approaching the same number, this is 0. Boom. Right? Nice and quick. Okay, what is the limit as z approaches infinity of, say, 2z plus I over z plus 1? Well, here I want to compute using the second fact, that if I replace z with 1 over z and compute the limit as z goes to 0, that gives me the limit as z goes to infinity of f of z. Okay, so whatever this is, this has to be equal to the limit as z goes to 0 of 2 times 1 over z plus I over 1 over z plus 1. Okay. But what is that? How do I compute this? Well, I can multiply both top and bottom by z, which leaves me with the limit as z goes to 0 of 2 plus zi over 1 plus z. Right? So the limit as z goes to 0, this thing is just 2 over 1, or 2. Okay. That's nice. Well, what about the limit as z goes to infinity? Let's do one more. So let's do 2z cubed minus 1 over z squared plus 1. What is this equal to? well, thinking about this in the same way, what if I looked at, this is going to be my last example where I'm actually going to look at the reciprocal of f of 1 over z, right? So I'm going to apply this one. So I'm going to look at the limit as z goes to 0 of reciprocal with 1 over z, replacing z here. So this is 1 over z squared plus 1 over 2 times 1 over z cubed minus 1. Right. So multiplying, say, both top and bottom by z cubed to clear those denominators. This is the limit as z goes to 0 of multiplying by z cubed here. This is z plus z cubed over 2 minus z cubed. And as z approaches 0, this numerator, of course, is going to 0. So this is 0. So if the limit as z approaches 0 of 1 over f of 1 over z is 0, that means that the limit as z approaches infinity of the original function is infinity. Okay. And so this is a useful way of computing limits using those rules, okay, and dealing with that point at infinity. Okay. So let's talk about the last topic I want to mention today, which is we have already noticed that if p of z is a polynomial, then the limit as z approaches z naught of p of z was easily computable from those limit rules as just p of z naught, right? Next, I want to consider all such functions f of z such that the limit as z approaches z naught of f of z is equal to f of z naught. Right, so this was true for polynomials. Polynomials are super nice. What other types of functions is this true for? What do we call a function that satisfies this? This is just the defining characteristic of a continuous function. So continuous functions are exactly those. Okay. All right, so I'll give the definition, restate the definition in terms of epsilon delta, and then I think we will be done with today's lecture. So, definition of continuity at a point z naught. Okay, so we say a function f is continuous at z naught, okay, if the following three conditions are true. So if the following conditions hold, so first one, the limit has to exist. So the limit as z approaches z naught of f of z has to exist. Secondly, f of z naught exists. So as a functional value, that exists. And lastly, the limit as z approaches z naught of f of z is equal to f of z naught. This is that condition that I had boxed on the previous page. Right? This is the defining characteristic of a continuous function. Okay. So if you're being short here, right? If you're careful with how you define these things, then this is all you need, right? This boxed thing is all you need. It actually contains the previous two. And if we recast this in terms of epsilon delta, what this means is that for every epsilon greater than 0, there exists a delta greater than 0 such that we have the modulus of f of z minus f of z naught is strictly less than epsilon whenever the modulus of z minus z naught is strictly less than delta. Okay. All right. So this is just replacing my previous notion of limit with the fact that this limit is actually equal to the functional value there. Okay. Another way of thinking about this, of course, is that you can move the limit through the function, right? That's kind of a nice way of thinking about continuous functions, is that they are exactly the functions you can factor limits through. Okay. And of course, continuous continuity, just as it is for a function of a real variable, is defined pointwise. So this is continuous at a point, z naught. We say that f is continuous on the set R if it is continuous at every point of R. So we define it pointwise, and then we say that it has that property on an entire set if it satisfies that property for every point in the set. Okay, so this is a pointwise definition here. Okay, so here's where we'll pick up tomorrow. All right. So your second homework I'll post later today. It'll contain, as I mentioned previously, examples of having you graph some of these functions as transformations, or plot the sort of transformations they are, or describe them, together with some basic algebra of limits. Okay, that's the main thing it'll focus on. It'll be due in a couple days. So anyway, I'll see you tomorrow. As I said, hopefully all of the lectures will be on time now. No more appointments or anything until a couple weeks from now. So anyway, I will see you all tomorrow. If you have any questions, email me. Otherwise, let me know, and I will send out an announcement when I post your homework. Okay, so I will see you all tomorrow.